Alrighty. Sorry for that brief interruption. Back to our show. So today we're going to just look at some ideas to try to motivate this concept of comparing things. The main computational thinking concepts will be employing our abstraction and pattern recognition. And the purpose is that in engineering, we often wish to ask questions about data and interpret the results. When we do that, we usually employ statistical methods that provide some characterization of confidence or likelihood about the answers. So is set 1, who has a mean value of 10, is its mean value statistically different from set 2, whose mean value is 100? I mean, 10 and 100 clearly being different numbers, but are they far enough apart to be truly different? And that general category of methods to help answer that question, or at least defend the answer, are called statistical hypothesis testing or significance tests. So that there's kind of the nomenclature. The material for today's lesson comes from mainly from these three readings that are here in the links. And we could ask a probability question. What's the chance of anyone visiting those in this room? Probably better than a great white shark coming through that door and biting me in my bottom, but not much. What is hypothesis testing? So hypothesis testing is a statistical method used in making statistical decisions about population using experimental data, which is called a sample. Testing is basically an assumption we make about the population parameter. So for example, you state, on average, students in this section are taller than 5 feet 4 inches. How would we test that conjecture? Got about 25 of us in here today, and we could measure everybody and then write down the measurements. And so what does on average more than 5 feet 4 inches mean in that context? There's 26 of us in here. We make those measurements. If on average they're bigger than 5 feet 4 inches, how many of those 26 would you expect to be 5 feet 4 inches and taller? Only one of them is 5 feet 4 inches and taller. Is your statement defendable? No, that's bullshit. If all of them are 5 feet 4 inches and taller, yeah. How about if 3 of them? Everyone's shaking their head no. Okay. 5, 7, 9, 12, 13. I got one yes in the back. So yeah, if there's 26 people, 13 would be exactly half are bigger than 5 feet 4 and half are not. In that case, would that statement be somewhat true? And if we had 14, we'd be really happy. We'd go home, call it a day. Other kinds of things. An average boy is taller than an average girl. How would you test that conjecture? We could round up all the males and females on the planet. Shouldn't be too hard. There's 4 or 5 billion of each, give or take a billion. And measure them, and then look at the mean value of the males, the mean value of the females. The mean value of the males is bigger than the mean value of females. We could probably comfortably conclude that men are a bit taller than women. But it's saying an average boy and an average girl. So how do we decide if they're average? We ask them a question: what's the airspeed velocity of the sparrow? If they don't answer with, do you mean an English or an African sparrow? They are clearly below average. We throw them into the fusion reactor and use them for fuel. And only get left with the 200 people on the planet that actually remember that Python and search for the society. It really wasn't supposed to go there. Or another similar question is a specific treatment. Say we've got vaccine A, vaccine B, vaccine C. Vaccine B is effective in treating COVID patients. Again, how do you test that conjecture? Try it on a bunch of people. Yeah, you take a bunch of people, you split them into two groups. You don't cut the people in half because they got bigger ones at that point. Just keeping the blood in them when you do that's tough. That saran wrap doesn't stick real good, so that's fine. So you divide them into two groups. One group you give the treatment, the other group you give something that looks just like the treatment, but really it's just narcotics. And wait, you count to see how many of each group is left alive after 2 weeks. The narcotics group, if you can even find them, because they're all going to run off. Has fewer people remaining than the COVID-19 group, you might conclude that the treatment is indeed more effective than narcotics. So that's literally all hypothesis tests are doing. It's how to take narcotics. But we've got to use a little science behind it to make sure that we can charge the otherwise high prices for the narcotics. So just a little bit more definition. Why do we use it? Hypothesis testing is an essential procedure in experimentation. The test evaluates two mutually exclusive statements about a population to determine which statement is supported by the sample data or the sample evidence. When we say that a finding is statistically significant, that is akin to saying that a hypothesis test was performed. So when you're on the TV news and they tell you that a certain political candidate is leading the polls by 20% plus or minus 0.3 of a point, somewhere there's been a hypothesis test done. But if it's on the TV news, you just have to assume it's bullshit though. Okay, so first we're going to examine comparing two collections. So I break hypothesis testing in this easy form into two kind of generic categories. We have two collections of things and we have a treatment. And they're essentially the same, but they have to be couched and presented slightly differently so we don't confuse ourselves. So first we're going to look at two collections. And I thought it was a good idea to actually use real data. I'm rethinking that, but we're committed here. So let's suppose we are presented with the interesting environmental engineering question. Does construction activity impact stormwater solids metrics? So when we build something, the usual way to do it is to tear up all the perfectly good land until the soil's exposed so it can see the sun and go hot, warm out its armpits. Then it rains and all that solids gets washed away into our nearby streams. And then someone from the EPA, because they've already shut down the Ghostbusters, comes by and wants to shut down your project. It's bad and it kills all sorts of hoppy things. So generally, it's not a good thing to have a solid washing off your site. Also, usually that solids has to be replaced, and so you're throwing away resources. So there's our back, and then there's a whole background. Clean Water Act. Let's see why would do this. Clean Water Act prohibits stormwater discharge from construction sites unless authorized by an NPDES permit. A permit is a fancy way of saying you've written a check to the necessary government agencies, multiple checks, in fact. Permittees must provide a site description, identify sources of contaminants, blah, 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 blah. The appropriate measures are further decided in 4 classes: erosion, sediment control, stabilization, structural practices, and stormwater manglement. Collectively, the site description is known as a SW3P. EPA anticipates that stormwater management will be able to provide for the removal of at least 80% of total suspended solids. TSS is used as an indicator to characterize the control of other pollutants. Therefore, solids control is critical to the success of any SW3P. So that's a background for this particular problem. Now, in this case, there was a construction site near NASA in the Houston area, and it was monitored briefly before construction started and then during construction. The construction was going to happen anyway. The monitoring was actually for something else, but it was a good opportunity to see if the stormwater pollution prevention plans actually had to do any work or not. And so there are two files called pre-con for pre-construction and durcon for during construction. And in these two files, we're going to go look at them in a second. It contains the information we have to work with to try to evaluate this question. Is there a difference? So first, but wait, there's more. We need a working, that'll work. So this particular lesson, you actually need to have a working notebook handy. I think I have one laying behind. I'm going to bring it into the playground. Everybody loves to go to the playground. And what it's going to contain is these blocks, and we'll go through it slowly. So you got to go away. There you go. All right, so the first part, we will import some packages. We'll import NumPy and Pandas and plotting library. Our task, remember, is still to analyze the two data sets and decide if construction activities impact stormwater quality in terms of solids measures. Then we'll go ahead and get the files, which are located here. Let's verify that they're not in the playground right now. We can prove that by attempting to read them. Sure enough, it's not. Run that. Yep, don't have the files yet. So let's go ahead and get them. Please work. Oh, sweet. So this section of script went ahead and just got the files, and you can do that on your own if you want. And now we will load in the two files and turn them into Pandas data frames. So there's pre-con and durcon. If we look at the header of pre-construction, we see that there's a date associated with each measurement. There's a column labeled ts.pre, which stands for total solids pre-construction. There's a column tss.pre, total suspended solids pre-construction. And there's rain.pre, which corresponds to the rainfall on that particular date, or the cumulative rainfall. So if we look at the pre-construction data, at least tabulating, bring your attention to the rainfall column. Most of the rainfall is less than 1 inch. You have 1, 2, 3 instances of something bigger than an inch, or an inch or bigger. If we play the same game for the during construction, we see that there's a few more observations. Same column headings, but with the DUR postfix instead of PRE. The rainfall has 1, 2, 3, 4, 5, 6, 7, maybe more, 7 instances of 1 inch or bigger. So you might conclude, well, geez, regardless what the results are, if it rains more in the during construction phase, of course I expect there to be more solids washed off. So one sub-question we might want to ask is the rainfall changed between pre-construction and during construction? If we look at the total solids or total suspended solids, the magnitude of the numbers there visually looks bigger. It looks like it's roughly 100 times bigger. So in terms of, so these are in the 100s and 200s, and these are in the thousands. So in terms of just a quick visual look, no brains required, the pre-construction and during construction indeed look like they come from different underlying processes. But let's explore that a little bit further. So here's the codes we've just run. Let's go ahead and describe the pre-construction. Help if I click on the right doodle. So here's our pre-construction. The mean value of total solids is 462. Total suspended is 286. Rainfall 0.87. The standard deviation of those three respectively is 361, 312, and 0.88. So we'll repeat that with the during construction and see what we can learn there. So to do that, we go back here, and because whoever authored this was kind enough to leave us cut and pastable stuff, we perform the miracle of cut and paste. And in the during construction, we see the mean value is 3,500, 2,700, and 1. So the ranges are pretty close in terms of the mean. The standard deviations are 7,000, 5,000, and 1.3. Those are bigger than the pre-construction phase. So can you argue that these are the same or different? That wasn't a rhetorical question. Somebody stick their neck out so I can lop it off. Okay, you claim they're different. So that begs the question. Okay, I agree on the context that the mean values are certainly different numbers, and it appears that they're a lot different enough that we can comfortably say that the two processes appear to be different. But let's go beyond that. Let's see if we can get some other ammunition in our argument, because this is for an investor. Let's just go straight to the total solids. Actually, I think I have it already there. So if we were to look at the rainfall distributions, okay, so we're not to the question we want to ask yet. Make it big enough to see. And we go ahead and plot two histograms of the rainfall distributions. Now remember, one collection of data had 16 things in it, the other one has 22. So they're not the same size. But the red histogram there that's in the background represents the pre-construction rainfall. And this is a density histogram, so this is just representing fraction of the total collection. The vertical axis, the horizontal axis is representing rainfall depth. So what's the largest pre-construction rainfall depth that we see represented by this histogram? Somewhere up here, 3.5. How about for the post-construction? We got a 6, we got something around 5, got something around 4. And then we got a bunch here on the left, just like the rainfall. Keeping in mind that the lengths of the two collections are different. visual look at that, they look kind of the same. The red one hasn't had enough opportunities to pick up its bigger values. So in terms of functional shape, those look kind of the same. Now clearly the red mean is going to be a little smaller than the blue mean. And we can find out what that is simply by looking up here. The red mean is 0.87. The blue mean is just a bit over 1. The red variance is 0.88. The blue variance is 1.39. So there's more spread to the blue as expected. But those aren't far apart. So again, without tools yet, we can say, yeah, they're different and the numbers are different, but the distributions kind of look an awful lot alike. So I don't know if they're far apart enough for not to say that they're different. Let's play the same game with total solids. Okay, so we're going to construct a similar kind of histogram. The code is down here with the big red arrows obscuring it. We'll do the pre-construction, post, or during construction. We're going to turn the density feature off, so it's not going to report counts instead of relative densities. That's some trial and error to make it easier to see. And we actually control the bin count to try to get enough resolution to learn anything. So if we do that, let's go ahead and run that sucker. We get that. So the red histogram represents the pre-construction information. We got a whole bunch down here, kind of close to 0. We got one instance somewhere up here near 1,000. We have nothing off to the right. Now during construction, again, we have a whole bunch here between 0 and 2,500. But we have non-zero instances here at 5,000, something here close to 10,000, something here in the 20,000, 25,000, 30,000. So in terms of mean values, it's pretty evident that the blue distribution is indeed different than the red distribution. And one way we can ask that question is, how many standard deviations away from the mean value of the red distribution is the mean value of the blue distribution? Which begs a further question: which standard deviation? We're going to use red standard deviations. How many standard deviations, red standard deviations away, is the mean of the blue from the mean of the red? Well, to answer that, we have to find what the mean value of the red is, which is 462, and the standard deviation is 361. Keep those numbers in your head. And then the mean value for the blue is 3495, and we'll ignore its standard deviation. So the distance between the two, 3495 minus 461. So that's the mean of 2 minus the mean of 1. So what is 34 minus 95 minus 461? It's roughly 3,000. Okay, let's just go there. So they're 3,000 units apart, and the standard deviation, if you recall, was 361. So we're 3,000 units apart. And if we divide by the standard deviation, that gives us 8 or 9 standard deviations away. So we're 8 or 9 standard deviations away from the blue distribution from the red distribution. Now, is 8 or 9 standard deviations? A lot of standard deviations are not very many. It's a lot. Pretty much, if the data are normally distributed, 6 standard deviations explains 99.99% of the data. It covers 99% of all the possible observations. We're at 8 standard deviations. So we're covering 99.9999% of all the observations. we have a disadvantage. We don't have stuff left zero because negative solids don't make sense. We could tell ourselves we don't really know what's going on. Let's try some simulation. Let's just pretend that these are normally distributed variables. Go ahead and simulate two different samples, assuming they're normally distributed, but I'm going to use the mean value from the pre-construction, mean value from the during construction, and the standard deviation from the pre-construction, and the standard deviation from the during construction. And I'm going to make 10,000 samples from a normal distribution that has those means and standard deviations. So we're going to call those two series pre-S and during S. And then we will go ahead and create a data frame from them. We'll name one column pre-sim, another one during sim. And then we'll call the data frame itself my fake data. Normally I just pick names to be funny, but in this case, the word fake is intentional. When we start doing simulations like this, you want to be sure that you're identifying your fake series versus your real series. So let's go ahead and do that. Make the data frame. And now we're going to go ahead and let's really crank up the bin count. And there are, actually, let's put it in density form. I'm curious to see what happens if I do that. So these will be relative frequency distributions, not counts. Okay, so we've now gone from blue and red to blue and orange. That's the default. What can you say about the pre-simulation distribution of our fake data? Where's it centered? Close to zero. How about the during simulation center? Where does that occur? About. Yeah, I think I agree with you. The center for the pre-sim is somewhere here. The center for the during simulation is somewhere here. So those two mean values are 3,000 units apart. We already know that. We could actually interrogate our distributions. So what are the chances that the mean value in during simulation, somewhere over here, could be a member of the pre-simulation distribution? Are they high or low? Okay, low, I agree with you. Now, how did you come up with that reason? Say that again? There's something more to it. What else? Let me keep the question in mind. I'm going to redraw the graph with a slight change. Hopefully I don't fuck this up. Actually, I don't really care because it's easy enough to fix. Same means as before. Mean here is somewhere around there. Mean here is somewhere around there. What are the chances the mean value of the orange distribution could have come from blue in that picture? It's high. In the other case, it wasn't. What was the main difference? Standard deviation. was that the blue distribution before was very narrow. It had a fairly small standard deviation. So the chance of the orange coming from blue in that instance were pretty low. There's no random way that that number could appear. The converse of that, asking blue from orange, is different because the standard deviation is so huge. Since we are our game, we do have the ability to play games right now. Let's put that back to its original case, and let's see a standard deviation of 7,000. If I drain it down to 700. And now let's suppose we had two collections, and that's what it looked like in distribution. What are the chances of something from the orange distribution possibly coming from the distribution? Pretty low. How do you justify that? I agree with you.
There's 2,000
Okay. That very quantitative way of stating it. Or the simpler way would be like, well, the blue distribution and the orange aren't anywhere near each other on the graph. There's a whole lot of nothingness between the two. There's a whole lot of Central America between the left coast and the center of power of politics in the United States. Although I think I have my color scheme wrong for that. Well, the blue is correct. This should be, no, this should be blue and that should be blue. Yeah, there's no red at all. Okay, so that's sort of the idea of a hypothesis test without actually doing it. Let's continue to play with the graphics just a touch longer. I'm going to try to shift the orange distribution to the left a little bit. I think that will accomplish it. So at this point, we're not talking original distributions anymore. We're making stuff up as we go. And rather than rebuild the data series, we're just changing parameters in the generating distribution. Oh, that's not a bad shot. That's pretty good. Okay, so now we have the case where our mean value in our orange distribution, the mean value in our blue distribution aren't quite so far apart. And if we were to ask the question, what is the chance that what we observe in the orange distribution came from a blue distribution? It's not pretty good. The blue distribution encompasses all the observations in the orange distribution. The relative frequencies are quite a bit different. And a number down here is unlikely to be seen in the orange distribution. But any orange distribution number is likely to be seen in the blue distribution. And so hypothesis tests are tools not to help us with the obvious case that we just had, where they were far apart, but to help us with a case like this, where they're not completely far apart. So there may be sufficient evidence here to conclude that orange and blue are indeed different. We would have to apply something more than these graphics here. Okay, are there questions? I think that ends what I want to do and gives us a chance to get over to the lab. Okay, so here's your lab. Good, it's coming up correctly. So the lab today is very much like what I just did here. Different collections of data, of course. And you're going to explore stuff with plotting tools, histograms, and such. And then the homework is actually quite easy for me because I've already done it. You have two collections, not very much, and you want to produce a histogram of the Amazon boxes, the Walmart boxes, decide if Amazon boxes are stronger than Walmart boxes. Yes, sir.
The instructor notes into the Lab 17, and the download from the page says no file.
You need to refresh your browser. Pardon?
It's not the HTML because that works. It's when you go to download the IPYNB. But I'll show you the 21th for the.
Okay, that one didn't get you. I guess you're gonna have to type this in the hard way. The syllabus links correctly? That is weird. See what's wrong with the URL. I wonder if it's supposed to have a hyphen right there. Oh, it's failing to accept input. Yeah, this stuff programs perfectly, and then your computers screw it up. Yeah, syllabus doesn't work. Okay, well, it'll be working by the time you start lab. Go find out what's wrong right now. That works fine. You were 5 minutes late.
Yes.
Mhm.
Did you give me the, or?
Yeah.
Okay.
That is bizarre as shit.